Hello everyone, welcome again to Modeling Methods and Mechanical Engineering, and we're going to continue our discussion on the finite differences method, FDM. And today we're just going to go over an example of how to implement the FDM in a multidimensional transient problem. So it's basically a direct extension of the formulation that we had shown in the previous class, where we discretize time and space. But in this case, we're going to discretize 2 dimensions of space. So this is here, modeling methods in ME. And we're going to talk about multidimensional, explicit FDM scheme. So it's just an implementation. We're going to just basically go over an example, and to illustrate this, we're going to try a 2-dimensional transient heat diffusion with heat generation. So basically we are going to be addressing a differential equation that looks like the Laplace of the temperature, and in this case we're going to say constant conductivity. Although that need not be a requirement, but we're going to do it in this case. So the Laplace of the temperature, which is a function of x, y, and t, plus some generation term UG triple prime, divided by the conductivity. Remember, the conductivity goes in the heat flux term in this part of the equation, but we just divide it over. We're going to assume that the generation is a constant, but again, that need not be a requirement. That can be also a function of space and time. 1 over alpha dt x, y, and t. So this is a heat diffusion equation. And to illustrate again this particular case, we are going to assume that the domain is a rectangular one. That goes from 0 to L in the x direction, and it goes from 0 to small l in the y direction. And we have some internal generation, UG triple prime, which we've said is a constant, but again, it doesn't need to be a constant. Let's assume that the heat flux on the left-hand side is imposed, so we have a second kind condition on the left-hand side. On the right-hand side, let's assume that we have some convection, so Q is equal to some imposed film coefficient, T minus T infinity at XL. It's also imposed, so we have some flow that's circulating at a temperature T infinity XL and has a film coefficient or heat transfer coefficient HXL. On the bottom, let's say that we also have a heat flux. We're going to call this QYO. And on the top, we are going to assume that the temperature is imposed TYL. So we have all 3 types of boundary conditions at all edges: second kind on the bottom and on the left, third kind on the right, and first kind on the top. Let's assume that we have an initial condition. Well, initial condition needs to be given because this is a transient problem. Txy of 0 is equal to T0. And again, let's assume that's a constant value. That need not be the case. Again, that can be a function of space. It can be a function of x and y. And in general, we're going to make it a function of x and y just to be more general in this illustration. So the boundary conditions, if we formulate the ones that are given here in the illustration, Q at x equals 0 is Q of x0. It's a given value. And what that means basically is that we've already gone through the formulation of the boundary conditions. That means that the partial derivative of t with respect to x at x equals 0 is equal to qx0 divided by k. Remember that q is minus k dt the normal. The normal vector here is -1, so it's minus k times minus 1 dt dx. And that just basically boils down to qx0 divided by k. All right, on the right-hand side, we have q at x equal L is equal to hxl t minus txl, t infinity xl, and that basically turns into dt dx at x equal L plus hxl over k times t at x equal L is equal to h over k, hxl over k, t infinity xl. On the bottom here we have q at y equals 0 is equal to q y0, and we go through the same thing, and this will end up being the t dy at y equals 0 is equal to q y0 divided by k. And finally, the temperature at y equal L is equal to T YL. And I just simply repeat that. T at y equal L is equal to TYL. So this is the first kind, Dirichlet, or fourth condition. So let's just frame all these boundary conditions. This is the first one. And that's it. Now, if we wanted to solve this problem analytically, what would we have to do? Well, we have a transient problem given by this equation. The equation is non-homogeneous. The problem is framed in the orthogonal coordinate system, L and L. And the problem is separable. And the problem has a non-homogeneous initial condition, and it has 4 non-homogeneous boundary conditions. So you would have to, in order to solve this problem, let's elaborate on this. To solve these problems analytically using separation of variables, a number of superpositions will need to be performed. So basically what we need to do first is let the temperature of x, y, and t, we went through this process last time, we separate that into a transient solution plus a steady solution. That's necessary because the governing equation itself is non-homogeneous. So what we do is keep the transient problem homogeneous. So basically this will make the Laplace of tt of x, y, and t equals to 1 over alpha dt dt of x, y, and t. And that would mean that the Laplace of t steady plus ug triple prime over k will be equal to 0. That will make the initial condition for tt equals to, so if t is equal to tt plus ts, then the initial condition for tt will be the initial condition for t minus ts. So that will be t0 at x comma y minus ts at x comma y. There's no initial condition for ts. And the boundary conditions, so we are going to keep all boundary conditions, so all boundary conditions homogeneous boundary conditions. And for Ts, we are going to move all the non-homogeneous boundary conditions here. Okay, so basically notice that all boundary conditions are non-homogeneous, so we are going to keep them all the same kind, but at equal to 0 for the transient problem, and then we're going to keep the non-homogeneous part of the boundary conditions in the transient problem. So basically, and the steady problem. So the steady problem is steady problem, but it has a non-homogeneous governing equation, and it has a set of non-homogeneous boundary conditions, all four of them. So now the transient problem, Tt of x, y, and t, is solvable directly by separation of variables. But Ts of x and y requires a number of superpositions, right? Because we can only apply separation of variables if the governing equation is homogeneous and if all but one boundary condition are homogeneous. So basically, we're going to have to let Ts of x and y be equal to some phi of x, which is the portion of the solution in which that is going to address the non-homogeneity on the governing equation. We've done that before when we have a non-homogeneous equation like that, plus a T1 of x and y, a T2 plus a T2 of x and y, plus a T3 of x and y. And I think that's enough, right? Because then we can keep T1 with all but one homogeneous boundary condition. We can then do T2 with all but the other non-homogeneous boundary condition, and then we can do T3 with all but the other non-homogeneous boundary condition. So 1, 2, 3, and I think we need a T4. We might. So then you have to solve 5 different problems in this particular case, which makes things extremely complicated. So this is a long and tedious process. So eventually, after solving these 6 problems, that's the one for Tt, the one for phi, T1, T2, T3, and T4, then you end up with the temperature being equal to T of T, the transient portion, plus a steady portion. And remember, you need to figure out what the steady portion is. You need to solve all of these first to be able to solve for T transient, because the initial condition depends on the steady solution. So, needless to say that this is a long and tedious process to have to be able to do this analytically. So instead, we are going to try the finite differencing approach. We're going to scratch all this, and instead of trying to look for an algebraic solution, we're going to look for a discrete solution. Instead, try an FDM approach. And we said that we're going to use the same explicit formulation, the same explicit scheme. And what we do is position the governing equation at Tn, xi, yj. So the governing equation would be basically the second derivative of t with respect to x squared at xi, yj, tn, plus the second derivative of t with respect to y squared at xi, yj, tn, plus ug triple prime over k, which is a constant, but if it weren't a constant, then we would position it xi, yi, yj, tn. No difficulties there. 1 over alpha dt xi, yj, tn, such that tn is equal to n times delta t, such that n goes from 0 to big N, and delta t is equal to some final time of calculation divided by n. Likewise, xi is equal to I times delta x, such that I goes from 0 to I, and delta x is equal to L divided by big I. and yj is a discretization of the vertical dimension, is j times delta y, where j goes from 0 to big J, and delta y is just simply L divided by J. And that's how you discretize space and time. So basically, what this second derivative with respect to space will end up being is simply t at I plus 1 comma j at time position n minus twice t at I comma j position n plus t at I minus 1 comma j at time position n divided by delta x squared. Then the second derivative with respect to y would be t at I comma j plus 1 at time position n minus 2 t at I comma j at time position n, t at I comma j minus 1 at time level n divided by delta y squared. Then plus UG triple prime over K is equal to 1 over alpha times T at I comma J n plus 1 minus T at I comma J at n divided by delta T. So again, we use a forward differencing approximation of the time derivative and central difference approximation of the two space derivatives. Okay, and this will lead to an explicit scheme. We're going to let f of x, the Fourier number, and the x direction be that. We're going to let f of y be alpha delta t over delta y squared. Right, so you know that's going to come up when we try to solve for Tij. And then Tij at n plus 1, n position, n plus 1, the next time level, is equal to t I comma j at n plus alpha delta t UG triple prime over K plus the Fourier number in the x direction times t I plus 1 comma j at n minus 2 t at I comma j n plus t at I minus 1 comma j at n plus the Fourier number with respect to y t at I comma j plus 1 position n, t at I comma j at position n, plus t at I comma j minus 1 at position n. And this, again, is an explicit formulation, meaning that everything on the right-hand side we know from the previous time level, starting from the initial condition, and that's how we can figure out what happens at every node on the next time level. So, basically, this is valid. This equation is valid for I going from 1 to I minus 1, j equals 1 to j minus 1, and n going from 0 to n minus 1. So essentially you can implement this at all time levels, right? But only at interior nodes. Interior nodes. So for the n nodes along the walls, let's go back to the original problem. Right here, we need to implement these boundary condition, this boundary condition, this boundary condition, and this boundary condition. So basically what happens is that at n nodes, so when I is equal to 0 and j goes from 0 to j, that would be in all the nodes along the left wall. Then use dt dx at x equals 0 equals qx 0 over k. And we know how to implement that in finite differencing. So basically take the forward differencing approximation of this derivative, right? And we've already formulated that before. At I equal big I, j from 0 to j, so at all the nodes that correspond to the right hand side wall, we will do dt dx at x equal L, for which we need a backward differencing approximation. So relate the derivative of the point of the temperature at the edge to the temperature right to the left of it, plus h xl over k t at xl is equal to h xl over k t infinity xl. At j equals 0, I from 0 to big I, so that will be the bottom wall. So at the bottom wall, we'll have to implement these boundary condition, and that is dt dy at y equals 0 is equal to qy0, some given value of the flux, divided by k. And finally, at j equal big J in all values of I, then we'll have t at y equal L is equal to t y L, the first kind of condition. So that we don't need to implement any derivative approximation, it's just the temperatures given as such. Now, one thing that you may notice is that, actually let's draw a diagram here of what the finite differencing representation of these domain would look like. So basically this will be I equal 0, I equal 1, this will be I minus 1, I plus 1, and this will be I equal I minus 1, and this will be I equal I. Same thing here. And this will be j equal 0, j equal 1. I would say, let's do it here, j equal, or j minus 1, j plus 1, somewhere in the interior. And this is under the assumption that there will be some nodes in between here, some nodes in between here, some nodes in between here, and some nodes in between here, here and here. So this will be j equal j minus 1 and j equal big J. Again, so this is the nodal representation, and again, if we wanted to find the temperature, for example, here, that temperature will be related to all the temperatures around it, namely these ones and these ones, right? But if we wanted to know what the temperature is here at the next time level, then we would actually have to use a completely different kind of topology, so the points are around it. There's no points to the left of that, and therefore we cannot use this expression. Because this expression refers, if you set a point ij, it will refer to the points to the right, to the left, above, and below. And some points do not have points to the left, some points do not have points below, so we need to use the boundary conditions for those. Also, notice that when we implement the finite differencing approach for the corners, for the edges. So for example, at I equals 0 for all values of j, so for all these nodes, we're including the corner nodes. So in this corner, for example, j equals 0, I equals 0, we are implementing this boundary condition, but we are also implementing this boundary condition. So we're implementing this boundary condition from the left and this boundary condition from the bottom. Now, because those two boundary conditions are heat fluxes, right? We have to take an average of the two. Right? We cannot have this temperature be related to two separate heat fluxes, because then we'll get two different values of temperatures at the next time level. Now, on the top, for example, at this corner, we're implementing this condition, but we're also implementing this condition. So we are telling that this node is governed by whatever this flux says, but this node is also given the temperature because there is a forced condition. So what do? Do we use an average? No. When we have a forced boundary condition, that will take precedence over everything, right? So, and all these nodes on the top, what would take precedence is the temperature boundary condition, right? And on the right-hand side, we have a third kind boundary condition. So, for example, in this node, what do we apply? The third kind boundary condition or the force condition? Again, the force condition takes precedence over everything. But on the bottom here, what takes precedence is the third kind condition will take precedence over the flux. So, first kind condition, first at corners, first kind BCs take precedence over second and third, and third kind condition BCs take precedence over second kind. So that's just a rule that you can use to do this appropriately. So we're going to implement this on MathCAD. See what happens. Obviously, we have nothing to compare with because I didn't go through the entire process of deriving that long analytical solution. So for implementation, let L equal 1 and L equal 1. We're going to let the generation be equal to 100. Whatever those units are, this can be meters, so this will be watts per meter cube. K is equal to 1, so this will be watts over meter Kelvin. Alpha, remember that's in meter squares over second. Let's make it 10 to the minus 3. Let's make the initial condition be equal to 0. Let's make the flux on the left-hand side be equal to minus 100 watts per meter square. The negative number means heating. You can do that by looking at the sign of the heat flux. It's minus k dt normal. So that means that the slope of the temperature gradient will be negative. That means that it's heating from the left. So a negative heat flux means heating. That's counter logic, but that's what algebraically mean. Let's make the film coefficient equal 1 and the convective temperature be 0. Let's make the heat flux on the bottom of the domain be equal to 100. So it's positive. That means that it's cooling. So this is cooling from the bottom, heating from the left, and it's actually cooling through convection from the right at a temperature of 0 degrees. Initially, the domain is at 0 degrees. And let's make the temperature, YL, be equal to 0. So the top is kept at 0 degrees. The initial temperature is 0 degrees, and we are cooling on the right at 0 degrees. So we try to maintain this cool, but it's being heated from the left and being cooled at a constant rate of 100 watts per meter squared from the bottom. So let's see what happens. Again, we have nothing to compare it against, but we hope that this will produce the right solution if it's formulated correctly. So let's check this out. So in this lecture, we are illustrating a multidimensional explicit finite differences method example, FDM example. These are the parameters that I actually just wrote. The generation terms 100, and SI units that will be watts per meter cube. K is equal to 1, and SI units that will be watts per meter Kelvin. alpha is equal to 10 to the minus 3. That will be meters squared per second. The initial temperature is 0. We are going to make delta T equal 1, so our time step is going to be 1 second. And we are going to advance this 1,000 time steps in time, or 1,000 steps in time. Okay, the reason I define this differently, rather than starting by saying, okay, I want to know what is the final time of arrival, is because I want to control the Fourier numbers. Remember that in theory, it's not in theory, in practice too, the Fourier numbers in an explicit scheme would have to be below 0.5 for the scheme to be stable. So I want to make sure that the delta t that I pick and the resulting delta x, delta y will provide me with stable Fourier numbers. Again, the length is 1 in both directions, so I'm going to discretize with 11 grid points, I equal 10 and j equal 10. So I'm going to have 11 by 11 nodes, that's 121 nodes. Delta x, the resulting delta x is 0.1, the resulting delta y is 0.1, and I discretize the horizontal space from 0 to I, and I discretize the vertical space from 0 to j. Again, the resulting Fourier numbers in the x and the y direction will be 0.1, so this technically will result in a stable scheme. I said that on the left we are going to impose a heat flux of minus 100. That means we're going to be heating at minus 100 watts per meter squared from the left. The film coefficient on the right is 1. The units of film coefficient in SI units is watts per meter squared Kelvin, for Newton's cooling law to be consistent. The infinite temperature, or the flow temperature, convective temperature on the right hand side is equal to 0. And the Biot number, which is h over k times delta x, is equal to this expression. On the bottom, we're cooling at 100 watts per hour. At the same rate we're heating on the left, we're cooling on the bottom, and we're maintaining the temperature on the top at 0 degrees. So the idea here is when we do multidimensional finite differencing analysis, at least in MathCAD, for example, this particular illustration, I am not going to keep track, and I'm not going to keep in memory all the time distribution, all the nodal distributions in time of the temperature, because that will overload the memory. Plus, MathCAD is funny with three-dimensional arrays. You will have to keep an array of t of I, j, n to be able to do this. And MathCAD sometimes doesn't like this. So what we do basically is formulate exactly the same scheme that we had before, right? First of all, fill out the temperature with the initial condition, right? And then advance in time, or iterate over time from n equals 0 to n minus 1, and then apply the equation, the finite differencing equation, at all the inner nodes from I equal 1 to I minus 1 and j equal 1 to j minus 1, right? Same thing that we did before, but that we have another nested loop for the vertical direction. So that's nothing new. But instead of filling out the same temperature at the next time level, I'm just going to create a new array called T new. This is the new temperature distribution at the new time level. So what we basically do every time we advance in time is to just basically overwrite the previous one. And therefore, we only keep, the only thing that we're going to return at the end of this algorithm is the final value, the final temperature distribution. The final temperature distribution over the nodes at the final time step, which we had already indicated will be 1,000 time steps or 1,000 seconds. To see if that's what we want to know, that's what we get. I'll change this value to show you the difference. Then I'll impose the boundary conditions. First of all, for I equals 0 and for I equal big I, so on the left and on the right, I impose the heat flux on the left and the convection on the right for all values of j except the corners. See, from j equal 1 to j minus 1. Then on the bottom, at j equals 0 and at j equal big J, for all the nodes except the corners, I impose flux on the bottom and temperature on the top. And then for the corners, at 0, 0, remember, I would impose an average of the two fluxes, qx0 plus qy0, which will end up being 0 because these two will cancel each other. In this particular case, one is heating and one is cooling at the same rate. And then for the top corner, top right-hand corner, top left-hand corner, and top right-hand corner, I impose a temperature because remember the first kind condition takes precedence over everything else. And on the bottom right corner, I impose a convective condition because that will take precedence over the second kind condition. So remember, first kind condition takes precedence over all conditions. third kind condition will take precedence over second kind condition. So when I return t, and t is just basically the last time step of this analysis, time step n. It's the new temperature. I overwrite t with the new temperature, and that's what I will return. That will be exactly after 1,000 seconds. And after 1,000 seconds, all I want to do is just show the temperature distribution. This is a contour plot of the temperature, right? As you can see, this is physically correct, right? So the temperature, there's energy being added from the left, so it's being heated. From the bottom, we're cooling, right? On the right-hand side, we're also cooling through convection, and the top is kept at 0 degrees. What it appears to be here is that we have temperatures under 0 degrees, and that's perfectly possible. See, I query here what is the explicit temperature. So when we return t, we return into an array called t explicit, and if we print t explicit, what we'll get is an 11 by 11 array of temperatures at the last time level, right? So what happens with that array is that it has values under 0 degrees, and that's possible because we're cooling through the bottom. So everything starting at 0 degrees, this is being not held at 0. The right-hand side wall is not held at 0 degrees. It's actually being convected at 0 degrees. But the bottom is being cooled at a constant rate of 100 watts per meter square, and therefore the temperature is being forced under 100 degrees. If I change the time evolution and say I only want to know this after maybe 10 time steps, what would happen to this domain after 10 seconds? Everything's starting from the same. The initial temperature is 0, but I want to know what happens after 10 seconds. And after 10 seconds, as you can see, the heating wave is coming in. It hasn't had enough time to penetrate, so this solution hasn't reached steady state. The cooling wave on the bottom has started to go in, but it hasn't reached the entirety of the domain, so this hasn't reached steady state. If I do this after 100 seconds, then the heating wave is penetrated a little bit more, and the cooling wave is penetrated a little bit more, but you see the maximum temperature is 39.9 and the minimum temperature is minus 27. If I keep advancing in time, 100 seconds, then the maximum temperature is 54 and the minimum temperature is minus 19.75. So let's see what happens after 5,000 seconds. So what numbers do we have there? Let me go back. 54 and minus 19. So after 5,000 seconds, 54 and minus 19. So it seems to have reached some sort of steady state condition, some asymptotic condition. Or if we go to 10,000 steps, this might take a while. Well, it took a couple seconds. The number is 54.766 and minus 19,273. So basically, we have achieved steady state. So this will be the trick to solve a steady state problem. Use the same algorithm. If I am given, like a homework problem, for example, or an exam problem, solve this problem, right? But we are told that this is steady state. How do I go about implementing this in a finite differencing approach if the problem is not steady? I cannot do, for example, the backward differencing or forward differencing in time because I don't have a time derivative. If the equation was this or were these, how do I solve that problem? Well, remember that any steady problem is basically the result of a transient problem that evolved to an asymptotic solution, to evolve to steady state. So basically, if we are given a steady problem like this, we just invent the right-hand side and let it advance in time all the way until it actually settles down. And it appears here that after 5,000 seconds or so, this problem has reached steady state because the temperature doesn't change. The contour distribution doesn't change, and the maximum and minimum temperature doesn't change. That means that the temperature field has reached steady state. And this is how we would solve a steady problem. All right. So that would be useful for some of the assignment questions and perhaps some of the exam questions. So keep this in mind. This MathCAD spreadsheet will be available to you to use. And that's it. That's all I wanted to cover on this particular lecture. And I'll see you next time.